Okay, at the end of the last session of the circle, I left you with this theorem, Raleigh's theorem. We saw some examples of it, and it was kind of startling, but we didn't have time to prove the theorem. And people asked me if I could record a quick sketch of it. It took me a few days, but here we go. So what the theorem said was that if you have two positive irrational numbers, alpha and beta, and the sum of their reciprocals is 1, then when you start looking at these sequences that you get by taking 1 times alpha, 2 times alpha, 3 times alpha, and taking the floor of each one of those, rounding them down to the nearest integer. They're never exactly an integer because integer multiples of an irrational number are going to be irrational. They're not going to be exact integers, but you round them down to the nearest integer. And then you do the same thing for beta, right? Beta is this other irrational, and the two numbers are related by the sum of their reciprocals being 1. But you do the exact same thing. You take 1 times beta, 2 times beta, 3 times beta, round those all down to their nearest integers. It's called taking the floor. And when you look at those two sequences, it turns out, and it's certainly the examples we saw all seem to look like this, that every single positive integer shows up on one of those two lists, but no positive integer shows up on both of those two lists. They partition the positive integers. Some of them are with the alphas and some of them with the betas, and nobody's with both. So just to remind you, the one example that we looked at was the square root of 2, and then if alpha is the square root of 2, and you take, you solve 1 over alpha plus 1 over beta equals 1, you find out that beta is 2 plus the square root of 2. And here you are, you look at their multiples and round them down to the nearest integer, and the multiples of alpha are on the left column, the multiples of beta on the right column, and 1 and 2 are on the left, 3 is on the right, 4 and 5 are on the left, 6 is on the right, 7, 8, and 9 are on the left, right? It doesn't go every 2, 1, 2 on the left, 3 on the right, 1, 2 on the, the next 2 on the left, 3 on the right. If that was the pattern, they would actually be rational numbers. But in fact here, because they're irrational, the pattern jumps, it's generally every third number is on the right, but every now and then it jumps up 4 numbers, like 3, 6, and then not 9, but 10, and then 13, and not 16, but 17, 20 and 23, not 26, but 27. But if you look at it, you'll see, this goes down to about 38 on the left side, but all the numbers from 1 to 38 are showing up there. Some of them are on the left and some of them are right. There's no repeats. You can verify that yourself. You can go to Wolfram Alpha and generate this table by yourself. And just to show you that it's nothing to do with square roots, here's one involving pi, right? So if alpha is pi, and then you solve 1 over alpha plus 1 over beta equals 1, and you discover beta is pi over pi minus 1, here are the multiples of pi on the left column, integer multiples of pi, rounded down to the nearest integer. 3, 6, 9, 12, they're going up by multiples of 3 because pi is just a little bit bigger than 3. But then when after 21, you don't hit 24, you jump to 25. And then it goes up by 3 again for a while, and eventually after 43, you go to 47. But if you look at the right column, you get all the numbers that aren't on the left column. So 1 and 2 are on the right, 3 is on the left, 4 and 5 is on the right, 6 is on the left, and so forth. And then when you hit that 24 that doesn't show up on the left, lo and behold, 22, 23, and 24 are on the right. So it seems to be working. It seems to be a theorem, and it is a theorem. So how do you prove a theorem like this? So the basic idea, and I already wrote it down, so maybe I should clear it and write it again. So the thing to think about is if I give you a positive integer n, how many multiples of alpha will be less than n? And just to make it concrete, I chose n equals 100 just so you could see what I'm talking about, but I hope you'll realize that the argument we're going to do here has nothing to do with the specific number 100. It would work for any integer. If you look at the numbers alpha, 2 alpha, 3 alpha, up to k times alpha, where k times alpha is the largest multiple of alpha, integer multiple of alpha that's less than 100. Of course, when you round it down to the nearest integer, it'll be at most 99 point something. It might be less than that. If alpha is big, they might be jumping up by 3 or 4 or 5 at a time. But k times alpha is an irrational number that's less than 100. So it's an integer plus a little bit of a fraction. The biggest it could be is like 99.999 or something. It can't be any bigger than that, because if it were, then when you if it were bigger than 100 and then you round down to the nearest integer, you would get 100. But k times alpha, the irrational number, is itself less than 100. When you round it down to an integer, it's at most 99. But then k plus 1 times alpha is bigger than 100. When you round it down to the nearest integer, it might also be bigger than 100, but it's certainly going to be bigger than or equal to 100. And similarly for j, right? We're going to take beta. we're going to take multiples of beta until we get to the largest multiple of beta that's less than 100, j times beta. And j plus 1 times beta is bigger than 100, right? Because beta is irrational, you're not going to hit 100 smack on the nose. Multiples of beta will be integers plus fractional parts, and eventually you hit one where the integer plus fractional part is less than 100. Then j plus 1 times beta, the integer plus fractional part is greater than 100. When you round down this integer, it might be exactly equal to 100, it might be larger. But if you just look at k times alpha and j times beta themselves, without the floors, they're definitely less than 100, and k plus 1 times alpha and j plus 1 times beta are definitely greater than 100. So we can solve for k and we can solve for j in terms of 100 alpha and beta, right? K, if just k times alpha is less than 100, just divide both sides by alpha. The integer k, right? K is an integer that you multiplied alpha by. That integer is less than 100 over alpha. But k plus 1 is bigger than 100 over alpha. Right, we're just taking k times alpha less than 100 less than k plus 1 times alpha and dividing all three of those by alpha. Similarly, j is less than 100 times beta, which is less than j plus 1. But we know even more. Now this is towards the bottom of the screen there. 100 over alpha plus 100 over beta is 100 times 1 over alpha plus 1 over beta. And we're starting with two irrational numbers where the sum of their reciprocals is 1. So 100 times 1 over alpha plus 1 over beta equals 100. So that tells me that k and j, k is the integer is less than 100 over alpha, and it's greater than 100 over alpha, that quantity minus 1. Is that clear? Because k plus 1 is already bigger than 100 over alpha. So just, if k plus 1 is bigger than 100 over alpha, subtract 1 from both sides. K is bigger than 100 over alpha, that quantity minus 1. And similarly, j is bigger than 100 over beta minus 1, but it's less than 100 over beta. So what does that tell me about k plus j? K plus j are both integers, and when you add them together, they're going to be greater than 100 over alpha minus 1 plus 100 over beta minus 1. That's 100 over alpha plus 100 over beta minus 2, which is 98 on the nose. So k plus j is greater than 98, but also it's less than 100, because 100 times 1 over alpha plus 1 over beta is exactly 100. K and j are both smaller than 100 over alpha and 100 over beta respectively, because 100 over alpha and 100 over beta are irrational numbers. You have to round them down to get to k and j. So k plus j is an integer, because k and j are, that is strictly greater than 98 and strictly less than 100. Hey, that's 99. And so there's exactly, if you look at the two sequences, 1 times alpha, 2 times alpha, 3 times alpha, up to 99 times alpha, or up to k times alpha, and 1 times beta, 2 times beta, 3 times beta, up to j times beta, there's a total of 99 numbers there, because k plus j is 99. So there's 99 numbers in the two sequences that are less than 100. Well, that's, 100 was an arbitrary thing. What I've really shown, that argument is perfectly general. You can do it with n's instead of 100. There's exactly n minus 1 numbers in the two sequences that are less than n. In particular, there's exactly 100 numbers in the two sequences less than 101. But wait, if there's 99 numbers in those two sequences that are less than 100, and 100 numbers in the two sequences that are less than 101, there's got to be exactly one number in the two sequences that's between 100 and 101. I'm going to type that down. Therefore has an E on the end. There is exactly one, that was supposed to be one number in the two sequences that is between 100 and 101. So, and similarly, there's exactly one number in the sequence, but give me any integer n, between n and n plus 1. If you look at the numbers, an integer times alpha, this times alpha, the next integer times alpha, the next integer times alpha, the next integer times alpha, and similarly for the betas, of those two sequences put together, there's exactly one number in those two sequences that's between n and n plus 1. That's the same thing as saying there's exactly one number in the sequence whose floor is n. And that works for every n. So there's a little bit to unwind here. I'm doing it quickly, but I think all the pieces are there. So I hope you'll think about that and verify for yourself that that really does work. Thanks.